Okay, so first derivative, right? If we're looking at a function, the first derivative tells us slope of the function, right? So if I've got a function that's doing this, then in this interval right in here, let's take it that point right there. Clearly, the first derivative is what? Positive, yeah, because the function's increasing, right? And it's walking uphill. Now, first derivative is pretty easy to keep track of once you start. But at this point, you guys are probably getting pretty good at that, and it's probably not a big deal to you to think in terms of the first derivative. We're going to shift gears now to the second derivative. And the second derivative, we've already done some stuff with the second derivative. You've calculated second derivatives. And Mr. Rickman, repeat your previous statement. What is the second derivative?
It's the slope of the slope.
Yeah, it's the slope of the slope. Right? It's the derivative of the first derivative. It's the rate of change of the first derivative might be the best way to think about it. So if we define, y prime, our first derivative is dy dx, well then the second derivative is the derivative with respect to x of the first derivative. Okay? Now let's think in terms of rates of change for a second. Why is it that a positive first derivative means sloping upward? Well, think about that. The rate of change of y with respect to x. If y is increasing in a positive way as x increases, then, can't we translate that in our minds, that concept, into an upward slope, right? Because y is the vertical position on the xy plane, and so if that's increasing in a positive way as we move to the right as x increases, we have to be walking uphill. And conversely, if y is increasing in a negative way, if dy dx is negative, then we got to be walking downhill. Now think about this though. What is the result going to be? Let's take the example of a positive second derivative. So the derivative, now the slope itself, is increasing in a positive way. For a slope to be more positive means what? If the slope is getting more positive, it's increasing in a positive way, what is that doing to the slope? It's getting steeper uphill, right? Does that make sense? Now, if there's another thing that could be happening, what if we were walking down a slope? And the slope is increasing in a positive way. Then what's happening? Oh, okay, it's getting less downhill steep, right? It's going to gradually start to turn upward, and if the trend continues, we're real steep. It'll get less and less steep, and then eventually it'll start to get uphill, steeper and steeper, right? Okay, so now what is that going to mean in terms of the shape of the curve? What does that correspond to in terms of like a topological feature like we've been talking about, peaks and valleys, etc.? What's going on? If the first derivative is getting increasingly positive, what is that doing to the shape of the function? If it's getting, we just said kind of the two possibilities. If the ant is walking downhill at that point that we're referencing, then it's getting less steep in a downward direction. If he's already walking uphill, it's getting more steep in an upward direction.
So zeros and pi?
Well, no, if it's, that's okay. If it's, you mean zero of the, which derivative, first or second?
Second.
Second, okay, we'll get there. The zeros are going to be, let's talk about what a positive second derivative looks like and a negative second derivative looks like. And then the zero is going to be kind of the transition between those two figures. So a positive second derivative, and that's really what I was just referring to. A positive second derivative is where the slope, the first derivative slope, is getting increasingly positive, right? It's increasing. So you tell me, maybe rather than have you describe it, could you just point out some places where that would be happening on this landscape, this function scape up here, right? If I've got, here's, somebody tell me a place up there where the first derivative is increasing in a positive way, aka the second derivative is positive? Can you point to a place?
The valley.
Okay, meaning, okay, so kind of in here?
Yeah.
Okay, that makes sense, doesn't it? Right? This area, this region sort of in here-ish, that would be a positive first or second derivative, wouldn't it? Because as the ant is walking downhill, the slope is decreasing. As he's walking uphill, the slope is increasing, right? Make sense? So we'll call that positive y double prime. Okay, now can anybody tell me a place, what do you think?
The really steep dip that when you're going up it, where the sharp corner is.
Right. I'll walk along, you tell me when.
You're deep positive now.
Okay, I'm getting positive second derivative or first derivative?
Second.
You think so?
No, because it's evening out instead of going up.
Okay, yeah, but there might be one other spot here where maybe we're,
Very,
okay, kind of right in here. It's sort of more, it's not as pronounced, but I'd say that it's sort of in this region right in here-ish. It looks like the slope is kind of, if it's a little bit negative, it's getting less negative, and if it's a little bit positive, it's getting more positive. Does that make sense? Let's talk about the other side of the coin though now. What if it's a negative second derivative? So that's a place where the first derivative is decreasing. It's getting more negative. So if an ant is walking down a hill, what's that going to cause to happen? It's going to get steeper down the hill, right? If you're walking this way. If he's walking down the hill, it's going to get even more negative and get steeper, right? If he's walking up a hill, what's that going to be doing?
It's going to get level out.
It's going to level out. It's going to get, if it's already pretty positive, it's going to get less positive, right? Okay, so I guess pink was our positive second derivative. Where would be some intervals where it's doing that stuff, where the second derivative's negative then?
the very start of the graph.
Okay, so kind of in here-ish, right? That's a negative y double prime.
And then the shape in the middle.
Yeah, it kind of even looks like in here, doesn't it? Like this area sort of in here looks like that's negative too, right? Okay, now what kind of generalizations can we say about this? How could we easily spot these places? And by the way, this is called the concavity. The behavior of the second derivative refers to the concavity of the function. We'd say that this is downward concavity. The green is downward. And the pink is upward. So we're supposed, what does that mean? If you had to explain that to somebody who was wasn't as mathematically as advanced as you guys are, what would you say then? Well, what's the shape of the curve where the second derivative is positive, for example? Upward concavity means what? Okay.
Smooth transition uphill.
Smooth transition uphill. Okay. You gotta even, if you're explaining this to your grade school nephews or brothers or sisters or whatever, you might even have to use less complex language than that. Yeah. How about something like bowl shaped up? Right? Where the function is bowl shaped up. In fact, one way you kind of think about it is if it's gonna catch virtual rainwater as it falls in our two-dimensional world up here, right? As the rain falls, if it's going to kind of pool up or catch, then it's concave up. If it's going to be shed, then it's concave down, right? So bowl up, concave up, bowl down, concave down. There is a little bit more mathematical way of always testing this that I think is pretty good. Look where a tangent line sits relative to the curve. Okay, so if I were to draw some tangent lines in the pink areas where we're concave up, where would those tangent lines sit relative to the curve? They're underneath. Good. So the curve is sitting on the tangent line when it's concave up. If I take a tangent line there, for example, notice that the curve is entirely above the tangent line. Same thing over here. If I take a tangent line, right? But in the areas where it's concave down, the opposite occurs, right? If I take a tangent line there, notice that the curve is completely below the tangent line. Does that make sense? Okay. So then where do you suppose then the zeros of, Maurice's earlier question, good question, where do you suppose the zeros of the second derivative would occur? Aha, yes. Where we're switching from, yeah, where we're switching, we're transitioning from concave down to up or vice versa, right? So here we're going from negative concavity to positive concavity, and if you have to look where that is, you can kind of eyeball it and get a pretty good idea. It looks like they transition right about, well, right about there-ish, don't you think? Okay. And then up here, it looks like we're transitioning, well, I didn't draw this very well, but I don't know, probably about there. Does that make sense? Give or take a little bit. And then let's see down here, it looks like maybe right about there. Okay. Those are called, those transitions of concavity or transitions of the sign of the second derivative, those are called points of inflection. That's a little wordy. We can also just call them inflection points. Okay, and then I'll call her quits today with that stuff. We just kind of got a conceptual introduction to this. Now, what we're going to do, I want to give you a little heads up. What we're going to do on, you know, you guys have done a really good job. Just take Monday off. Don't even bother coming to school. We'll just meet up on Tuesday. On Tuesday, we'll yeah, go ahead. Go ahead.
Oh.
On Tuesday, what we'll do is we're going to add another row to our table, and we're going to look at a different test called the second derivative test. And just kind of strategically, before I even cover it, I want you thinking about strategy, because that's ultimately, like, we get to 3-6, it's just, I'm just going to have you guys, I'm just going to say, here's a function, analyze it. And you're going to tell me all kinds of stuff. You're going to tell me intervals where it's increasing, decreasing, inflection points, relative extrema, horizontal and slant asymptotes, vertical asymptotes. You're going to put all that stuff on your table and in your sketch. And then real quickly you get an idea of what all the interesting features are in a function. The second derivative test, it's like when you can use it conveniently, it's a better test than the first derivative test. It gives you more information for less work. And on our table, remember on our table where we start off with, here's kind of our overarching strategy when we're using this technique. We go from X, the first row, then Y prime, and then Y double prime. You always want to work as far down the table as you can. It's most efficient to work further down the table. That gives you the most bang for your buck. Now, sometimes the second derivative test is just not worth doing, because calculating the second derivative sometimes is a real bear, in which case we just don't mess with it, and we instead we're satisfied to work on the third line, use the first derivative test. But we're going to come up with a really cool, efficient way of finding topological features by focusing on this row, and that's what we talked about on Tuesday. Okay? All right. Good deal. I'm done for today.